Hello, welcome back. We have been talking about electromagnetic induction, and now we're going to look at devices that we can use that have inductance, and we can put them in a circuit. They're called inductors, and what the reason that they're useful is that they can actually store energy in their magnetic field. There are two types of circuits that have inductors that we're going to look at. One is an LC circuit. That's a circuit with an inductor and a capacitor. And the other is an LR circuit. That's a circuit with an inductor and a resistor. Let's start by first understanding a little bit more about these inductors. A coil of wire or solenoid can be used in a circuit to store energy in the magnetic field. Inside a solenoid, we know that the magnetic field strength is B equals mu naught, the constant, times N, the number of turns, times I, the current, over L, the length. So based on that, we can define the inductance of a solenoid having N turns, length, L, and cross-sectional area, A, as the inductance being a capital L. So we put capital L for inductance. Inductance of a solenoid is equal to the magnetic flux divided by the current. Now we know that the magnetic flux is equal to B dot A, where B is the magnetic field strength, times A, which is the area. And that would be BA sine of 90 in this case, because those are perpendicular. So it's BA over I. Now that would be for just one loop, but we have N turns, so we're going to multiply this by N. So now we have N times B times A divided by I, and we're going to take our expression for our magnetic field strength inside a solenoid and put it in here. And so we now have N times mu naught Ni over L times A over I. Well, the I's cancel, the currents cancel out, and we can group our N's together with N squared. So we end up with mu naught N squared A over L. So we see that the inductance of a solenoid is mu naught N squared A over L. So it is proportional to the square of the number of turns, and it's proportional to the area divided by its length. Now that's the inductance. So the inductance has units of what we call henries. That's the units for an inductor, for the inductance, and it's 1 capital H, and that's equal to 1 Weber per ohm, per ampere, 1 Weber per ampere, and that equals 1 Tesla meter squared per ampere. A coil of wire used in a circuit for the purpose of inductance is called an inductor. And the way that we write this in a circuit, the circuit symbol for an ideal inductor is this kind of spring-like looking squiggly line here. And it's actually appropriately looking a little bit like a spring. We'll get to that later. All right, let's start to look now a little bit more closely at this inductor and see how it is possible that it is able to store energy in the magnetic field. So here we have an inductor coil. There's our inductor coil. And we see that we have a current coming in at the left. So it's going around our inductor coil like this. So there's our current going in at the left and coming around through our inductor coil. And if we take our right hands and we put them and we curl our fingers in the direction of the current, we see that our magnetic field will be pointing to the left. So here in this case, what we see in this figure shows a steady current into the left side of an inductor. So there's a steady current coming into the left side of the inductor. And in this case, we have the solenoid's magnetic field will pass through the coils, establishing a flux. So we have the magnetic field going through the coils. So now we have our magnetic flux, where again, our magnetic field is perpendicular to our coils. So now let's look instead at what would happen if we no longer had a steady state, a steady current. So in this figure, just like the one before, but in this time, the current into the solenoid is increasing. So this time it's increasing. So here goes our increasing current. And this time it's increasing. So it's increasing in this direction. And we know that because we use our right-hand rule again, so the magnetic field due to this current will be going in this direction. But that field is increasing, it's getting bigger. So this field is increasing. So what will happen is that, so as we have the current going in that direction, we have this flux that is to the left. And that means that we have this increasing flux. It's an increasing flux in this case to the left. So the flux is increasing to the left. So by Lenz's law, we know that we must have an induced magnetic field that opposes the change in flux. So the induced magnetic field must oppose the change in flux. So it will need to go to the right. And that's what these blue arrows here represent. So in order to have a magnetic field that goes to the right, if we take our handy right hands and we put our thumb in the direction facing right and curl our fingers around, we see that our current would need to go in the opposite direction. It'll go in this direction. And so the induced current is opposite the solenoid current. So therefore, the induced magnetic field must point to the right, and the current must go from right to left. The induced current is going to go from right to left. And the induced current will carry positive charges to the left and establish a potential difference between the positive on the left and the negative on the right, which is opposed to the potential difference that was before. So before, we would have had the positive charges going over here. That's what due to current going from left to right, and a negative on this side. So what we see is the induced EMF, delta L, so delta V sub L, must be opposite to the current in the solenoid. So we can write that as delta V sub L is equal to negative L di dt. Now let's look instead at what would happen if we have the current decreasing. So now in this figure, we still have our current going in the same direction. So going from left, around here, to the right. And so it's taking this current here is taking positive charges over here and has negative charges over here. And so this current, again, will give us a magnetic field that is going to the left. But this time, that magnetic field is now decreasing. So the magnetic flux is decreasing. So now, to oppose the decrease in flux, we need to have an induced field that goes in the same direction. So now these blue lines, that's our induced magnetic field, will also be going to the left. And so our induced current will also go in the same direction as we had as the initial current, as the input current. So it's now going in the same direction. And the induced delta V sub L is also going to be taking positive charges over here to the right and negative charges on the left. And so it will be adding to the potential difference. So the potential difference across the inductor measured along the direction of the current. In this case, if we look at the direction of the current, the potential difference, delta L, in this case will be negative L di dt. Where in this case, the current is decreasing and our potential difference would therefore be the opposite of that. So it would be increasing. So let's look at this compared to what happens in a resistor. Let's look at what happens to the voltage across an inductor versus the voltage across a resistor. So on the left, we have what we're getting pretty used to is our resistor. And we remember that Ohm's law tells us that that delta V equals IR. And in fact, as we go across the resistor, that is negative. We drop, right? We say we drop in voltage as we go across the resistor. That's the drop in voltage. So anytime we go across the resistor, the potential always decreases. Now in an inductor, as the current's going across, what we see is that the change in the potential across the inductor will depend on the sign of the change in the current. So if the current is increasing, that means that di dt will be greater than 0. And if di dt is greater than 0, that makes the right side of the equation negative. So delta V sub L will be less than 0. So the potential will decrease if the current is increasing. Now, if the current is decreasing, that means that di dt is less than 0. And that means that the right side of the equation will now be positive. So delta V sub L will be greater than 0. And so we see that the potential increases if the current is decreasing. So let's now look at the energy in the inductor. So as the current passes through an inductor, the electric power, as we remember, is P equals IV. P electric equals I times delta V sub L. Now we know from before, from what we just saw, that delta V sub L equals negative L di dt. So we can plug this in for delta V sub L right here. And we see that in that case, the electric power is equal to negative Li di dt. So this tells us that the electric power is negative because the current is losing energy. So the current is losing energy, so the electric power is going to be negative. Now, the energy is being transferred to the inductor. It's not getting lost, it's actually getting transferred to the inductor, which is then storing the energy, UL, at the rate dUL dt. And so that will equal a positive Li di dt. So now we can find the total energy stored in the inductor by integrating. So if I integrate both sides of my equation, I can pull L out in front because it's not a variable. That's the inductance. So I di dt is my integral. So I'm going to have L times I di dt. I'm going to integrate from 0 to I. And so that'll give me L times I squared over 2 evaluated from 0 to I. And so that gives me L I squared over 2. And so I see that the total energy stored in an inductor is going to give us 1/2 Li squared. So now let's look at the energy inside the solenoid. We know that the energy inside a solenoid, the magnetic field strength, we know is B equals mu naught Ni over L. We saw that. And we used that and we found that the inductance of a solenoid is mu naught N squared A over L. So now the inductor's energy can also be related to its magnetic field strength B. And so we start by taking that expression we saw before for the energy. So UL is equal to 1/2 Li squared. And we know that L is equal to mu naught. Put this in here for L. And so we get L is equal to mu naught N squared A over little l. So this then equals 1/2 times mu naught N squared A over L, little l, times I squared. Now, what I can do when I have my mu naught N squared A over 2L, let's put the 2 inside there, times I squared. Now, what I can do here is I can multiply by mu naught L over mu naught L. So I'm just multiplying by 1. That's really just multiplying by 1. And so I can then see that in that case, in the numerator, I'll have mu naught squared N squared I squared. All of that over in the denominator, I'm going to have an L squared. And I also will still have one over 2 mu naught times A times L. So now, I'll make that easier to read. So now what I can do is go through and we know that AL is the volume inside the solenoid. That's the area times the length. So that's going to be the volume inside the solenoid. So if we divide by AL, so that's the energy divided by the volume. And so we divide here by AL as well. So that will cancel there. What we're left with is the energy over the volume, and that is the magnetic field energy density, the energy per meter cubed, the energy per volume. And so we write this as U sub B equals 1 over 2 mu naught. And this quantity right here, the reason that we did this was to get this quantity right here, which we see is B squared. Because B, we remember, is mu naught Ni over L. So the energy density is 1 over 2 omega naught times B squared. So let's look at the comparison between energy in electric and magnetic fields. So in electric fields, we see that it's a capacitor that stores energy. In a magnetic field, it's an inductor that stores energy. In an electric field, the energy is 1/2 C delta V squared. In a magnetic field, the energy is 1/2 Li squared. Now the energy density in the electric field is UE equals epsilon naught over 2 E squared. And the energy density in the magnetic field is 1/2 omega naught B squared. So they compare fairly similarly. And one of the main things we see is that the energy density has the constant epsilon naught for electric fields, and for magnetic fields, our energy density has the constant mu naught. And they're both then multiplied, this one by E squared and this one by B squared. And that will be interesting to see later. Now let's see what happens when we put one of these inductors in a circuit. So the first kind of circuit we're going to look at are LC circuits. That means that we have an inductor and a capacitor. So over here we have our inductor, which we have with an L for its inductance, and a capacitor here, which has a C for its capacitance. Now, the initial charge is just going to be a Q naught. So that's going to be the total Q that we have on our capacitor. And here we see that the figure shows a capacitor with initial charge Q naught, an inductor, and a switch. So the switch closes at time t = 0. So the switch has been open for a long time. So there is currently no current in the circuit. Now, at time t = 0, the switch is closed. So what we want to think about, what we're going to ask ourselves, is how does the circuit respond? So what we find out is that the charge and the current will oscillate in a way that is analogous to a mass on a spring. We're going to look at that in some more detail here. We're going to look at that in a little bit more detail. So let's start with the very first step initially, right at t = 0. This is step A, right at t = 0. The capacitor will be discharging, it will start to discharge until the current is a maximum. So here we go. Initially, we see that we're going to have the capacitor will start to discharge, and we'll start, our current initially was nothing, but it's starting to increase. So now the capacitor is discharging, and the current is increasing across the inductor. This is similar, the analogy here is that this is similar. This is the maximum capacitor charge is like a fully stretched spring. So when the string is in its fully stretched position. Now let's look at the next step. What happens next? So now the current, here we go, here's our current, and it's going along. And it continues until the capacitor is fully recharged with opposite polarization. So here goes our, the next step is where the current is going to reach a maximum up here. And at that point, at point B here, we'll see that the capacitor charge at that point will be 0. So the inductor current will reach a maximum when the capacitor charge is 0. And then it will continue in the opposite direction until the capacitor is fully recharged with opposite polarization. And that's just like right here at this point. So we're now right here at this point where we have a maximum velocity. And so right now, maximum current occurs, and that's like having the block at maximum speed. So right there, it's going as fast as it can and going in the opposite direction. Now the next step happens. Now the discharge goes in the opposite direction. So now we have the charge and it's totally in the opposite direction. Now we have negative Q naught. So now we have all the negative charges on the top plate before they were on the bottom plate, and all the positive charges are on the bottom plate before they were on the top plate. And so right at this point, I = 0. Again, there's no current right at that point. And so let's see what that looks like. This is at point C. We've got it indicated right here. So right here, the charge is at the exact opposite charge, negative Q naught. And we see that the current at this point is right here at 0. So the current is now at 0. And this is like when we've got our spring has now been fully compressed and we've stopped the motion. The motion is 0 right at that moment when the spring is fully compressed. And that's where we are right now in our circuit. So now in the next step, now the current is going in the opposite direction, and it will again continue until the capacitor charge is restored back in the opposite direction. So in this case, we're now at point D, and at point D, that's where the charge is now 0. And so when the charge is 0, that is when our current is at a maximum again, but in the opposite direction. And so it will continue until it gets back to the point where the charge is back to Q0. So that is like the spring passing back again at maximum velocity, right in between. And that's exactly the point we are in this circuit. So we just saw the full circuit, and what we see is that an LC circuit is an electric oscillator that's going back and forth between positive Q0, Q0 and negative Q0. And the current is going between its maximum speeds in both directions. The charge in the upper plate is Q equals Q0 cos omega t. We can see that it's a function of cosine. And the current through the inductor is a sine function, and it's equal to I naught. It's equal to I max sine omega t, where omega is equal to the square root of the square root of 1 over LC. So now let's look at another type of circuit. So that's a LC circuit. Now we're going to look at an LR circuit where we have an inductor and a resistor. Now here, the switch has been at this position for a long time. At T0, it is going to be moved to here to position B. So this is T0. So now we have just the inductor and the resistor. So this figure shows an inductor and resistor in series. Now, initially, there is a steady current I naught being driven through the LR circuit by an external battery. That's over here. So initially, we have this external battery that is driving a current through the circuit. At T0, the switch is closed. How does the circuit respond? So the current through the circuit will decay exponentially with a time constant in this case of tau equals L over R. And so we see that unlike an RC circuit, where tau equals RC, in this case, tau is inversely related to the resistance and directly related to the inductance. And so similarly to an RC circuit, in an LR circuit, we will also see the current decaying exponentially. And so it will look like this, and we'll have the current starting at I naught, decaying exponentially as it decays with its time constant tau, where tau again equals L over R. So that is what an inductor is. It's able to store energy as a magnetic field. And we see that when we have an inductor in a circuit, it acts as an oscillator, an electric oscillator inside the circuit. And the two types of circuits that we've looked at are LC circuits, that's an inductor and a capacitor, and LR circuits, and that's an inductor with a resistor.